2.3 is about techniques for computing limits algebraically. And the first part of 2.3 in the book, you'll find this. It talks about where you can break limits up. And it says that if the limit of the limit as x approaches a of f of x and the limit as x approaches a of g of s both exist, then these properties you can use. The first one is the sum property. It says, fancy, the limit of a sum is the sum of the limits. But what that means is if I take a limit as x approaches a of f plus g, I can break that limit up, and I can take the limit of the first thing and add the limit of the second thing. And the nice thing about these is it's pretty much everything. You can take the limit where you add things. You can take the limit around where you subtract. If you multiply a function by a number, you can take the number outside the limit. Just take the limit of the function. If you take the product of two functions, you just multiply the two limits. The quotient of two functions, you divide the two limits. Now this part here, provided that g of x isn't equal to 0, this just makes the fraction make sense, because you can't have 0 on the bottom of a fraction. You can take limits in powers, so the limit of f to a power is the limit of f raised to that power. Notice that fractional powers are also included, and the square root of x is x to the 1/2. So fractional powers include roots as well, so you can take the limit inside roots. And that's really all the limit laws tell us, is that we can take the limit inside pretty much everything. And so here's an example that illustrates that. It says, assume that the limit as x goes to 1 of f is 8, and the limit as x goes to 1 of g is 3, and the limit as x goes to 1 of h is 2, and then find these four limits. And the idea here is you can use the properties above to take the limit to get the limit of the functions alone. And the first one, a, is the constant multiple property. What's happening in a is the number 4 is being multiplied by f. But the constant multiple property says that you can take limits and factor out that constant. And I know what the limit as x approaches 1 of f of x is. That limit is given above, it's 8. So the answer to this is 4 times 8, which is 32. B uses the property that you can take limits inside of powers. Here I have, in part B, I have the limit as x approaches 1 of h of x to the 5th power. Well, that property tells me that I could just take the limit of h of x and raise that to the 5th power. And that would be the limit as x approaches 1. You can take the limit inside powers. And we know what the limit of f of x is as x approaches 1. As x approaches 1, the limit, this is h of x, not f of x. So I'm taking the limit as x approaches 1 of h to the 5th power. That's the limit of x approaches 1 of h, then raised to the 5th power. The limit as x approaches 1 of h is 2. And 2 to the 5th power, 2, 4, 8, 16, 32. 2 to the 5th power is 32. Here I can break the limit up first around the quotient. So this is the limit as x goes to 1 of f of x divided by the limit as x goes to 1 of g of x minus h of x. But in the denominator of this thing, remember, you can also take the limit around subtraction and addition. So I can break that limit up in the bottom further and take the limit as x approaches 1 of g minus the limit as x approaches 1 of h. And when I write in these limits, the limit as x approaches 1 of f is 2. The limit as x approaches 1, the limit as x approaches 1 of f is 8. The limit as x approaches 1 of g is 3. And the limit as x approaches 1 of h is 2. So this is 8 over 1, which is 8. So this limit here, when I break it up first around the quotient and then around the subtraction, gives me 8. And D is the same idea. I can take the limit inside the 3rd power because you can think about this as a fractional power. This is f of x, g of x plus 3 to the 1/3 power. That's why I can take the limit inside the root, because it's really a fractional power. So I'm going to leave it as a root. Doesn't really change anything. That's just to show you that it's really a fractional power, so I'm using these properties. But when I take it inside the root, I get the limit as x approaches 1 of f and g plus 3. And since I can take the limit around a product, that's the same thing as the limit as x approaches 1 of f times the limit as x approaches 1 of g plus 3. The limit as x approaches 1 of f is 8. The limit as x approaches 1 of g is 3. So this is the cube root of 27, which works out to be 3. So all this does is tell you if you know the limits, you can take a limit inside pretty much everything to work it out. So that's a good way to practice these properties, but notice the properties are pretty exhaustive. Most anything you can throw a limit around or inside. Now when you're actually finding limits, now here I was given the limits. They told me what the limit of f and g and h were. They gave them to me out loud. But what happens if I don't know what those limits are? What if f, g, and h are written down like functions? And that's what the next part is how do you find the limit of a given function? And the easiest way is to just plug in and see if it works. And if you get an answer that makes sense, then that's the easiest way to do the limit. And so these examples here are all examples of me being able to plug in the limit. If there's no problem with it being undefined, or you don't get weird values like infinity over infinity, then you just plug in to write the answer down. In this case, I can plug in x equals 1 to figure out where this thing is at there. And so, replacing every x in here with a 1, I end up with 2 minus 3 plus 4 plus 5, which is 8. So I just plugged in 1 for x. And the same thing in part B. In part B here, x approaches 1. That won't make the bottom 0. So I can replace all these x's with the number 1 and get the answer to the limit. I can just evaluate. Now the reason I can do this is because the function is what we call continuous here. There's no weird holes or anything causing problems with vertical asymptotes in the domain. So we'll talk about that in a couple sections. But what happens is, here I can plug in because it's continuous, and I get 5 plus 6 plus 1 over 8 minus 4, which is 12 over 4, which is 3. So that limit, the y value of that function, turns out to be 3 as x goes to 1. It's continuous there, so I can just plug in. The same thing here for C. For part C, I just replace all the b's with the number 2. This is always the best way to start it. See if this works, because it's the easiest way to work it out. If it doesn't work, then there's other techniques we can use to try to make it work. So I replace all my b's with 2. I get 6 on top. I get the square root of 9 minus 1, which is 6 over 3 minus 1, which is 6 over 2, which is 3. I just plugged in 2 for b and evaluated to find that limit. So that's the easiest way to do it. If you can plug in the values like we've done here, then you can just come up with the limit without too much trouble. Now the problem happens when you can't find the limit this way. When you try to plug in and it doesn't work. And usually that's when you get zeros in the denominators of fractions. And it also happens with infinity sometimes later on. What happens when you can't plug in? Well, you try factoring and canceling common factors, and then evaluate. Or you simplify the fractions, and then you evaluate. The idea here is to factor and cancel, simplify as much as possible. So sometimes you got to use both of them. And so in the following examples, we're going to actually find ones that we can evaluate and that we have to work a little harder to get answers out for. So this first one, x squared minus 1 over x minus 1, the limit as x approaches 1. Notice if I were to plug into this thing, I would get 1 minus 1 over 1 minus 1, which gives me a 0 in the denominator, which is bad. So I can't just plug in. Plugging in does not work for this problem as it stands. But I can simplify this. And I can simplify it by factoring. I really can't simplify the fraction itself. It's just one single fraction. But I can factor x squared minus 1 into x plus 1 times x minus 1, because it's a difference of squares. And the bottom is an x minus 1. But notice when I factor, it cancels the x minus 1s in the denominator. And so these are really the exact same thing, just in simplified form. It turns out to be the limit as x approaches 1 of x plus 1. I can evaluate this. I don't have a problem anymore with plugging in 1 for x, because when I simplified it, it canceled that 0 in the denominator. And so the limit here is going to work out to be 2, but I had to simplify first to find that limit. The same thing in b. In b, when I see this, I notice when I plug in 3 on top, I get 9 minus 6 minus 3 over 3 minus 3, which is 0 over 0. Again, it's bad when I try to plug in. So instead, I try to simplify as much as possible, and then plug in. And I can factor the numerator. The numerator factors into x minus 3 times x plus 1. And note the x minus 3 factors cancel, and now I don't have problems with the denominator anymore. The limit as x approaches 3 of x plus 1 turns out to be 3 plus 1, which is 4. So that limit works out to be 4. And again, I had to simplify the fraction with one step to make it work. C is more of the same, but C is a weird one. C is just a tricky one to factor. If you look at the bottom, you see x minus b. So I'd like to cancel that x minus b, because when I plug in b, I get 0 over 0. When I plug in every x gets replaced by a b. I end up with b minus b to the 50 minus b plus b over b minus b. That's what I end up with if I replace every x with b, which is a big 0 over 0. So when I cancel this, I need to get an x minus b factored out of the top. So that's what I'm going to do. I'm going to factor out an x minus b because that's what I want to cancel. Well, there are 50 x minus b's in this first term. 50 of them. I canceled one out. So there's only going to be 49 x minus b's left. This is an x minus b in itself. So this is a negative x plus b. So I have to factor out, I better do this in 2 steps. First, I need to turn this into an x minus b so I can try to factor it out. And so what I have to do first is factor out a negative 1. Now you can stop to notice that if I were to take this negative 1 and put it back in, I would get negative x plus b, which is exactly what I have over here. So it's a legal factoring. But since I've done that, now I have 50 x minus b's in the first term here, and 1 x minus b in this term. So if I factor out an x minus b, I have 49 x minus b's in the first one, and there's a 1 in front of that one. So there'd be a 1 that's left over here. And this is the limit as x approaches b. But now I can cancel the x minus b factor, and I have the limit as x goes to b of x minus b to the 49th minus 1. Then when I actually go and evaluate this, I can plug in now. I can replace all the x's with b's, and I get, there is no 0 in the denominator anymore because I got that to factor. So I replace x with b, and I get b minus b to the 49 minus 1. That's 0 to the 49 minus 1. That's just the negative 1. So that's a really tricky one, and the tricky part is first factoring a negative 1 out to get an x minus b, and then factoring an x minus b out to cancel it in the denominator. Let me also talk about E first, before I go back to D. In problem E, there's 2 ways to do it. And so let's talk about way 1. The way 1 to do problem E is a fancy factoring thing. If you realize that x minus 3 is really the square root of, or x minus 9 is really a difference of squares if you write it the right way. So this is just an algebra trick that you either recognize or you don't. So you can think of x as the square root of x squared, and you can think of 9 as 3 squared. So you can factor x minus 9 into the square root of x plus 3 times the square root of x minus 3. Now, if you don't believe me, you can FOIL these two things together and see what you get. Square root of x times square root of x is x. I'll get a 3 root x and a negative 3 root x, which will add to 0. 3 and negative 3 will give me 9. A totally legal factoring. It's just weird to see. It's not usual to think of x as the square root of x squared. But if you notice this factoring, you can cancel the x minus 3's. And you're left with the limit as x approaches 9. On the top you have a 1, and on the bottom you have the square root of x plus 3. Now I can evaluate by actually plugging in. So I'm going to replace all my x's with the number 9. And I get 1 over 3 plus 3, which is 1/6. So one way to find that limit is to factor x minus 9 as the difference of squares. There's another way to find this limit. The other way to find this limit is to use something called the radical conjugate. And so I'll make d go away. We'll come back and see d in a moment. But way 2. The radical conjugate is like the complex conjugate. You change the sign in the middle is the easiest way to do it. So here I have the limit as x approaches 9 of the square root of x minus 3 over x minus 9. I can multiply the top and the bottom by the radical conjugate. And that just means you change the sign between the number and the square root. That's one way to do it. Now notice I get root x plus 3 and root x plus 3. If they cancel, you get a 1. So I didn't really change the function at all. It's really just multiplying by the number 1. So I have the square root of x minus 3 over x. Oh, whoops. I'm going to actually multiply these together now. And you have to FOIL when you do it. Square root of x times square root of x is x. The inner is negative 3 root x. The outer is positive 3 root x. And the last is negative 9. On the bottom, when I FOIL these together, I can just leave them this way, because I know in the end I'm trying to cancel the x minus 9 out of the bottom. That's the whole reason why I'm doing this. So I don't really need to FOIL the bottom out, because I'm trying to cancel the x minus 9 away anyway. But if you notice on top, plus root 3x and minus root 3x add to 0. So this limit, and this is what the radical conjugate does, it lets you cancel the 1 in the bottom. And it's another version of that factoring technique. I just have x minus 9 on top, x minus 9 times root x plus 3, and the x minus 9's cancel. And so I get the limit as x approaches 9 of 1 over the square root of x plus 3. And just like before, now I can plug in 9 for x. And when I do such a thing, I get 1 over 3 plus 3, which is 1/6. Same limit we got before, just a different technique to find it. So you can choose either of those two ways. If you're good at seeing the algebra, that's the fastest way to do it. However, the radical conjugate always works, and it really allows you to do the same limit. But in both cases, the limit turns out to be 1/6. Now I want to go back and do the one that I erased, because it's kind of a good one. So let me erase this first way to do this, and I'll go back and do the limit as h goes to 0. What's the limit as h goes to 0 of 1 over 5 plus h minus 1 over 5 over h. And if you look at this problem, you should see right away that you can't plug in 0 for h. This is actually a difference quotient. We'll be using these type of things in a minute, or in a few sections. So if I put h here, I get a big 0 in the bottom of the fraction. So I can't plug in. So what I'm going to do is simplify by putting the fractions together into a single fraction, so I can divide. And a common denominator here is 5 times 5 plus h. So I'm going to multiply the first one by 5 over 5, so I can get a common denominator. And I'm going to multiply the second one by 5 plus h over 5 plus h to get a common denominator. It's still all over h. This is just so I can find a common denominator. And so I get 5 over 5 times 5 plus h minus 5 plus h over 5 times 5 plus h all over h. I still can't plug in 0 because that h is still on the bottom. But I can add these two fractions together. So I get the limit as h goes to 0 of 5 minus 5 minus h. If you'll notice, that negative sign distributes to both of those terms. Over 5 times 5 plus h, because that's the common denominator. And the whole thing is divided by h. I still can't plug in 0 for h because that h is still in the bottom. So I have to do some more work. I simplify a little bit more. The limit as h goes to 0, the plus and minus 5 add to 0. So I have negative h over 5 times 5 plus h, all divided by h. But that h on the bottom is really an h over 1. So I can divide these two fractions by multiplying by the reciprocal of the denominator, which is 1 over h. And here the h's cancel. And so now that pesky h that was messing us up in the bottom is gone. I have the limit as h goes to 0 of negative 1 over 5 times 5 plus h. But now I can plug in 0 for h. And so I get negative 1 over 5 times 5, which is negative 1 over 25. So that limit works out to be negative 1 over 25. And you can find that limit by simplifying the fractions and reducing. So all those are examples of limits that you have to simplify a little bit before you can actually find. I also want to talk a moment about one-sided limits and then the squeeze theorem. So there's really only two more topics. So again, you can move the limit all over. So if I tell you what the limit is equal to, you can move the limit around to find limits. That's what the first examples were. The second examples were the easier limits to find because you can just plug in. And the later examples are limits that you have to either factor, or use the radical conjugate or factor, or simplify fractions before you can evaluate the limit. So the last limit topic is one-sided limits. These are limits of piecewise functions that are different on the two sides. So for example, here's a piecewise defined function. It says that f of x is x squared plus 1 when x is less than negative 1, square root of x plus 1 if x is greater than negative 1. And the problem is asking about the limit as I go towards negative 1, which is where these two functions are glued together. So the first one is the limit as I approach negative 1 from the left. Well, if I'm approaching negative 1 from the left, I'm smaller than negative 1. So I'll be using the function x squared plus 1. So if I want to figure out what this limit is, I'm going to have to plug my negative 1 into the x squared plus 1 function, because that describes what the graph looks like when you're smaller than negative 1 to the left. And so this works out to be 1 plus 1, which is 2. So this limit here works out to be 2. The second one asks for the right-hand limit. The limit is f of x. The limit of f of x as x approaches negative 1 from the right. Well, when I'm approaching negative 1 from the right, I'm bigger than negative 1, so I'm going to have to use the function square root of x plus 1. So I'm going to plug in my negative 1 in for x underneath the square root. And this is the square root of 0, which is 0. So the left side limit is 2, the right side limit is 0. Since those are different, the overall limit doesn't exist, because I need the plus or minus on that negative 1 to know whether it's from the left or right. They're different depending on what side you go to. So one-sided limits of piecewise functions especially, you can evaluate, and if they're equal, you can that's what the limit will be. If they're not equal, the limit doesn't exist. And the last one is the squeeze theorem. The squeeze theorem says that if you can stick a function between two other functions, then you can get the limit by squeezing it between the two other limits. And one of the examples in the book says that it can be shown that negative absolute value of x, so what you do is you bound your function and you take the limit of each side. So the first one says that you can show that x sine 1 over x is between negative absolute value of x and positive absolute value of x. And they want you to find the limit as x goes to 0. In all honesty, we have no techniques for finding limits of trig functions at the moment. And notice if I plug in 0 for x, it'll make this the sine of 1 over 0, which doesn't make sense. So I don't know what this limit is at all. But I can find the limit of the absolute value of x at 0. I can plug in 0. So what I do is I set up my function, negative absolute value of x less than x sine 1 over x less than or equal to absolute value of x. That's what they gave me. And I said, since I want to know about the limit as x goes to 0, I'm going to take the limit of all three sides of this. Limit as x goes to 0 of negative absolute value. Limit as x goes to 0 of x sine 1 over x. Limit as x goes to 0 of absolute value. Well, I don't know what the middle one is. But I know that when I plug in 0 on the outsides, because I can evaluate those, I get 0 less than or equal to the limit I'm looking for, less than or equal to 0. The only number in the whole wide world that's greater than or equal to 0 and less than or equal to 0 is the number 0. The number 0 is the only one that fits in there. So I squeezed my limit between two limits I could find. So I've proven that the limit as x approaches 0 of x sine 1 over x equals 0 by the squeeze theorem. I've squeezed it between two functions and found the limit of those. And so let me do one more of these, just another example. We can show that 1 minus x squared over 6 is less than sine x over x, less than 1. Use the squeeze theorem to find the limit as x goes to 0 of sine of x over x. So what I do is I take what they gave me, and I write the limit as x goes to 0 in front of each one of these things. So there's the 1 minus x squared over 6. Here's the limit I'm looking for. Limit as x goes to 0 sine of x over x. Less than or equal to the limit as x goes to 0 of what? Well, the middle one I don't know. But the outside ones I can figure out by plugging in. So I plug 0 into the first one. I don't know the limit in the middle. That's the one I'm trying to find. When I plug 0 in for x into the number 1, there are no x's there. So the number 1 just sticks around. And 0 squared over 6 is just 0. So I get 1 here, the limit I'm looking for, and 1 on the right. And the only number that can fit inside here and make it make sense is the number 1. So I've shown that the limit as x approaches 0 of sine of x over x equals 1 by the squeeze theorem. I've squeezed it between two functions I already know.